So it is a pleasure to see people here today. If I could ask students to please turn your webcams on if you can, that would be appreciated so we can have a more interactive and fun seminar. And it's a pleasure today to welcome Rose Abramoff. Rose comes to us from the University of Maine in Orono, where she's an assistant professor at the School of Forest Resources. She got her BA at Amherst College and a doctoral degree at Boston University. She's held postdocs at Oak Ridge National Lab, Lawrence Berkeley National Lab, and I'll probably say this incorrectly, le Laboratoire des Sciences du Climat et de l'Environnement, but I'm not sure where that was. Let you chime in, Rose.
It's just south of Paris. You said that fantastically.
Okay, that sounds nice. And she's going to be sharing with us her work in a seminar entitled Double Feature, Soil Carbon and Environmental Justice. And yeah, if you could join me, and again, turning your cameras on so we can see you. Grateful to those of you who have already done that. Thank you. And join me in welcoming Rose. Thank you. Dr. Abramoff, and hand it off to you.
Thanks, Juliet. Can everybody hear me okay? I'm assuming, great, I see a thumbs up. So I was told that I'd have about 40 minutes, and I thought that it might be the most fun to try and give two basically 20-minute talks that are somewhat related to each other in that they start to grapple with some of the more political and economic implications of the work that I've been doing. So I'm going to talk first a little bit about soil carbon sequestration and some of the considerations that I've had to increasingly think about as they relate to carbon markets. And then in the second part, I'm going to transition a little bit into kind of what we might be able to do as a community to protect scientific integrity going forward, and hopefully leave some time to just sort of hear where people are at and what they need, and maybe provide some resources for people who are feeling a little unmoored and maybe want to think about how they can build power as a community of researchers. Okay, so my background is mostly forest ecology and soil carbon modeling. I've done a lot of work primarily with kind of computer simulations of how soil carbon will change under different conditions, like under future climate or under different land management practices. I didn't put too many pictures up of that because it's like that's the most boring photo if you can see my cursor. But I do often get roped into field work and measuring gas fluxes and decomposition of litter and root growth through tubes installed in the ground, and all of that's a lot more fun. So those are the photos that I put up. And so the first half of my talk is really kind of under the auspices of my role at the University of Maine and the Department of Soil Resources, and then I'll sort of shift later on into this concept of environmental justice, which brings a lot of the perspective that I've gained from working as a community organizer and a climate activist, which is a lot of work that I've done over the last 3 years with a variety of groups, and in that one, I'm really not going to affiliate with the University of Maine, but really more so with the groups that I organize with. So I'm on the board of this group called the Climate Emergency Fund, which raises money and makes grants to climate groups, as well as an organizer with a group called Scientist Rebellion. So I can bring in some of my perspective from that. But let's start with the science bit and work our way there. So I probably don't have to talk to this group about the sort of relative technical infeasibility of staying under 1.5 at this point, which puts us into the danger zone of really most of these positive feedbacks. So I think this is a nice paper from a couple of years ago that sort of summarizes and within the paper it gives some nice kind of probability distribution functions of when at what global temperature warming factor above pre-industrial temperatures, some of these events become more likely than not. So like, abrupt boreal permafrost thaw, collapse of our large land ice sheets. And a lot of these things are, already underway to some extent. And I think, this group probably knows that about 80% of the greenhouse gas emissions that cause global warming is due to the burning of fossil fuels. But the other remainder of that, 13 to 21%, is due to the way that we use our land. So that's agriculture, forestry, and other kind of land management and use types. And I like to put up this kind of old graph just to show the sort of extent and use of the land that human civilization has sort of gone through throughout the years. So, for thousands of years, we've used much of the arable part of the Earth's surface in fairly extensive ways for either cropping or grazing or both. And there was a nice paper in 2017, that tried to estimate the carbon loss from these land use activities. So specifically from soils, sort of how much soil carbon have we lost over the last 12,000 years of human land use, with a focus on cropping and grazing. And so first what they did was they created a map of the distribution of cropping and grazing, and they looked at modern cropping and grazing here to just get a sense of the extent, and then used a soil model to estimate the change in soil organic carbon in the top 2 meters of soil over the long land use history, using a data set of land use, sort of the best knowledge that we have of land use, which is called the Hyde data set. And you can see that in that lower figure, there's a kind of distribution function where the more red colors represent losses of soil carbon in this top 2 meters profile, and green, lighter colors represent gains. And in general, there's more losses than gains, particularly in the places that have been intensively used by humans. Western Europe, you can see the Corn Belt of the United States there in red, near the lakes, and in China, and lots of other, places as well. And it really represents a potentially large carbon loss, which is one of the reasons why in the more recent IPCC report, when they look at mitigation options, there's a whole section, agriculture, forestry, and other land use, that looks at ways to basically put that carbon back into the soil as a potential mitigation of human-caused emissions. So this is just part of a really busy figure from the IPCC report that looks at mitigation options in multiple categories. And so, the first set of mitigation options are energy, which are fairly straightforward. Solar and wind represent mitigation options because they can be used to generate energy rather than using fossil fuels. And then there are a number of other sort of less carbon intensive energy generation options. So there's this whole section of potential things that we can do by restoring ecosystems, improving sustainable forestry, reducing food waste, et cetera, that have to do with land management that can contribute to reducing our emissions. And the one that I want to focus on for the next 10 or so minutes, maybe 15, is carbon sequestration in agriculture and their mitigation potential. One of the things that I think is interesting to note when you're just looking at this graph is that a lot of these mitigation options have really large error bars, and they represent our real uncertainty in how possible it is to mitigate emissions at global scales using these various methods. And we'll get into that a little bit. The other axis that I think is kind of interesting to look at when you look at this figure is looking at the colors. So up here in the right-hand corner, there's a legend that shows you the relative cost. So the darker red are more expensive costs, and the yellow is relatively less, 10 to 20 US dollars per teragram of carbon dioxide equivalent. And the blue is actually when the costs are lower than the reference, which means that, for example, wind and solar energy, it's actually cheaper than extracting coal, oil, and gas if we were to get rid of the subsidies that we currently have for them. So in some ways, by simply removing subsidies in certain sectors, we can accelerate a transition to clean energy, which is already in some ways cheaper than traditional energy sources. But a lot of the things to do with agriculture and forestry do have costs associated with them. And so it is important to consider those because monetary costs are one thing, but they often also have emissions costs as well. Okay, so how would we increase carbon stored in soils? Well, there are a couple of ways to do it. You can increase carbon inputs, and this is often in the form of cover crops or crops that we grow and then leave without harvesting, or by harvesting very not as intensively, so that we basically grow roots, we exude like carbon compounds into the soil. The plant material eventually dies and gets incorporated and becomes part of the organic matter stored in soil. So we're basically growing plants and we're leaving them there so that they add to soil. You can also add compost, which is adding carbon, nitrogen, and other nutrients to soils, or you can even add no carbon at all, but just add like nitrogen and phosphorus fertilizers, which can improve the productivity of plant growth, which fixes carbon dioxide from the atmosphere from photosynthesis. So there are sort of a lot of methods that have to do with, in general, cropping and amendments to increase inputs. Other ways that you can increase carbon stored in soil is by decreasing outputs. So you can, limit erosion and runoff into waterways where carbon might be more easily mobilized and transported back into the atmosphere. You can reduce decomposition. So one of the most popular in the agricultural sector is either no tillage, reduced tillage, or sometimes called conservation tillage, where basically by maintaining the structure of the soil and not breaking it up, you reduce soil decomposition, because soil microorganisms are living in all of these little films on these edges of soil pores, and by not breaking that structure up, you're not allowing microorganisms to access, that organic matter that they want to eat, or access pockets of oxygen or pockets of water. It's basically just kind of, creates a little maze with which not everyone's able to get all of the things they need to do metabolism. And by mixing soil up, you're sort of homogenizing it and allowing a lot more activity to occur. And so that's an often very popular way that that policymakers will ask farmers to try and increase soil carbon in their land, is by reducing tillage or not tilling at all. Okay. I want to talk a little bit about what sequestration is defined as in this context. So, as researchers, we tend to think very narrowly of like, okay, we're storing carbon by increasing carbon concentrations or increasing carbon contents or increasing the organic matter layer in our soil. We sort of think of it in terms of chemical or physical quantities. But there are also kind of three major kind of benchmarks that you have to satisfy in order for markets to be able to say, okay, like you've stored more carbon here. And they're sort of generally defined as additional, durable, and verifiable. So that the carbon that you add has to be new. So for example, it can't be, well, I'll go through an example, but essentially the carbon that you add has to be something that wasn't going to accumulate anyway, right? So that the intervention that you're doing has an effect. It's not just going to happen. You also have to, the carbon that you add has to be durable. It has to stay for a certain period of time. And in most carbon markets, this is usually a really arbitrary definition. It's often defined at about 100 years, which you can tell is kind of an arbitrary definition that's just based on a human lifetime and a round number. And so we can sort of talk about how useful that is. Because you could define it as 1,000 years, but it would be very difficult to prove that carbon lasts that long. And then it has to be verifiable. We have to be able to measure it within some certain uncertainty bounds. Okay, so I want to like talk a little bit more about each of those three, like satisfying each of those three benchmarks. So one of the interesting things about adding carbon that is additional is that it's often very hard to prove. So this was a group of social scientists in one of the kind of nature family journals called NPJ Climate Action. They did this survey where they basically asked farmers why they were engaging in practices to receive carbon credit payments, their motivations for adopting those practices, their concerns, et cetera. And there was one, interesting finding that I'm just going to read. So they found that while participating farmers were aware that the practices that they adopted, like no-till, for example, made them eligible to receive carbon credit payments, participating farmers' decisions to adopt these practices were universally driven by on-farm concerns. And what that basically means is that most of the farmers who are signing up for these credit programs, who are signing up to say do no till or reduce till, we're going to do that anyway. Like, we're already interested in reducing tillage for reasons of, increasing soil biodiversity or increasing water retention, or we're themselves interested in the sustainability and carbon storage of their land, which is great, and we should definitely incentivize those things, but it does sort of remove this benchmark of additionality, because it's basically like saying, why pay someone to do something they were going to do anyway. So that's always something that we try to think about when we're doing research for for people trying to design these sorts of programs. The other thing is durability. Durability is something that a lot of soil scientists are really interested in studying. We often try and define the age of soils as a kind of average, but in reality, soil has many different kind of functional groups, and they all have different ages. So, for example, you can separate soil into these kind of different functional groups, like organic matter that's stuck onto mineral surfaces, organic matter that's aggregated into clumps with little bits of rocks or little bits of microorganism, like the dead bodies of microorganisms or fungal mycelia, or invertebrate castings. Versus like particulate matter that's just partially decomposed leaves and whatnot. There are all of these different kind of chemical and biological constituents in soil, and they all have vastly different turnover times. And so when we dig into that a little bit deeper, we can start to define kind of general ranges. So this graph here on the right is work from a colleague of mine from 2017, where she basically looked at two fractions of soil, a kind of heavier fraction and a light fraction. Now, when soil is heavy, when it floats to the bottom of a liquid of a known density, it's because it's associated with something heavy, like the organic matter is stuck to a piece of rock, right, a mineral surface. And so we generally classify this dense fraction as organic matter, which is sorbed to minerals. And she used radiocarbon dating to try and understand how old it was. So this radiocarbon value doesn't relate directly to ages, or it's quite controversial to relate it directly to ages, but basically what you need to know here is that the more negative it is, the older it is, typically. And so she found that the dense fraction, particularly at depth, was much older than this kind of lighter particulate fraction of organic matter that's just partially decomposed. And this does sort of make sense in a way, like if carbon is stuck to mineral surfaces via like really strong ionic bonds or even covalent bonds or like ligand, like cation bridging, there's a lot of like interesting bonds that you can make with different types of minerals. It can be very, very difficult for that carbon to be broken off or to be metabolized in some other way. So some of that becomes very, very old. And so a lot of carbon markets are really interested in trying to increase the carbon that's stored in this particular fraction. So there are certain like initiatives that try to, like, for example, like sprinkle mineral dust on soils and whatnot, that might work in some ways and might have some negative effects on like soil nutrient availability or pH in other ways. So one of the issues with trying to figure out, I'm going to skip that slide, trying to figure out how much carbon you're adding and of what type, is that our soil carbon models, we have a lot of them, and they're all like have varying levels of sophistication, but they all pretty much they only agree within a general order of magnitude of how much carbon you would need to add to increase carbon storage by a certain amount. And so this is a work done by a postdoc I was working with a couple of years ago, where she looked at 16 cropland sites across Europe that were adding organic matter to their crop sites, trying to see how much carbon they could increase. And they had a particular target in mind. It was this: by increasing carbon storage by 0.4%, which they called 4 per mil. It's this kind of pan-European initiative to try to increase soil carbon by as much as it would take to offset anthropogenic emissions, which they calculated as this 4 per mil value. And so to reach that benchmark, they tried to figure out, okay, how much carbon do I have to add to my soils? And we can come up with an average value, which is actually quite high. It would require kind of more fertilizer than we can really spare in most situations. But you can just see from these bar charts that each of these pairs of bars represents one soil model, and they all have vastly different predictions across these 16 cropland sites. And you can also tell from their error bars that for each site, and if you read this paper, you can sort of look at the predictions per site. Each site has vastly different predictions as well. So it becomes a little bit of a challenge to decide, okay, what quantitative framework am I going to use to award carbon credits? Because if you chose one model versus another, farms could be receiving, vastly different amounts of money in order to do the amendment that we're asking them to do. So there's still a lot of uncertainty here. And I have a couple more considerations to add. So one of the things that I think is really interesting about the concept of soil carbon markets in general is that it tries to take a really dynamic system and make it as old as possible, which to some extent sets up this incentive to try and make soil carbon inert, right? To keep it from decomposing. But soils are made up of invertebrates and microorganisms and, fungi, plants, and they exchange with waterways and the atmosphere. And when they're functioning well, like that's how they work. They're these very dynamic ecosystems. They're much more dynamic than fossil carbon reserves, for example, which are meant to just kind of stay there for a long time and be incredibly old. We also have a bit of a tussle with industry about where to set the baseline. Often people will say, oh, okay, we want to increase soil carbon from where it currently is. But a lot of us now would like to argue that we should probably try and restore soil carbon contents from the last 12,000 years of human agricultural use before we start then trying to replace fossil reserves, right? Because we're already in a bit of a debt to nature that we would have to repay before we tried to start replacing fossil fuels with it. It's also important, I think, when we're thinking about what kinds of amendments to implement, that we're not just thinking about carbon, because soils serve so many other functions that are incredibly important to human welfare, like food production, water treatment, biodiversity stewardship, prevention of erosion, etc. I'll talk in the next couple of slides a bit about costs and incorporating indirect emissions as well. And then the sort of last thing I wanted to say about this more conceptually is that we want to make sure when we're implementing these systems to make sure that we're not allowing buyers of credits to delay reductions in direct emissions, because we can mandate that. For example, we can say, okay, we'll sell carbon credits for emissions that can't be reduced, or for energy streams that can't be changed over to renewables. We have not mandated that yet. So the way that the system is currently set up, it can be quite easy for buyers to use the purchase of carbon credits to delay in direct emissions reduction. And by direct emissions, I mean direct emissions of fossil fuel reserves. It's also often quite important to think about where we're getting the land that we're using for offset activities. For example, large multinational companies have bought up certain parcels of the Amazon to set up palm forests, which store a lot of carbon because they grow incredibly quickly. But some of those forest areas have been used by, indigenous people for subsistence agroforestry. So there are sort of justice implications to appropriating land for these activities that we also, need to think about. So, okay, so those are just kind of like the holistic considerations behind behind soil carbon sequestration as an industry. And as researchers, I study these sorts of things, and I think it's important. Like, I think a lot of researchers don't like to think about the economic and political implications of this work, but I think it's really increasingly important because we can't really escape uh, what happens with the models that we make or the research that we do. Okay, so the last concept I wanted to introduce, which maybe you're already familiar with from previous talks in this series, but I'll just go through it quickly, is this concept of a life cycle assessment or analysis, which is basically just a way to systematically analyze the environmental impact of some, often it's a product, but it can also be a process or any other activity. And so these, I'm going to skip some of these examples. Here's a nice example. Okay. So one example I think is really useful is enhanced rock weathering, because it actually does work under some conditions. So the biophysical process is basically that you go to a rock quarry, you quarry up some rock of a silicate mineral, you grind it up and sprinkle it on your crop. This looks like a corn crop in this cartoon. And silicate minerals react with carbon dioxide to form carbonates, which are this kind of inert, they're basically limestone that wash into the ocean and sort of sink to the bottom of the ocean and get stored fairly stably over geologic timescales. It's actually a fairly benign amendment that doesn't affect the ecosystem in as dramatic of a way as, for example, adding like iron filaments to the ocean would do. However, this type of amendment only stores carbon. The sequestration potential of this amendment depends on how much energy you're using to grind and transport the rock and where you're getting that energy from. So for example, if you're using diesel fuel to do all your grinding and transportation, then the benefit can often be outweighed by the direct emissions cost of driving that rock from the quarry to the site where you're amending it. And so there have been studies, for example, like in Brazil, saying, okay, if you're about 350 miles away from a quarry, it's no longer useful to do this sort of amendment. And so this is just one example. There's another soil carbon storage company, a startup that is like a personal pet peeve of mine, because they have all of these funky ideas of how to store wood residue that don't appear to have life cycle analyses associated with them. So one of them, for example, here in the lower right is this idea of like, okay, we're going to take wood residue, we're going to put it on a diesel like tanker, and we're going to sail it to Antarctica and then leave it there where it won't decompose, because Antarctica is cold. And while biophysically they're right, Antarctica is cold, the diesel fuel alone or like digging a giant hole and then burying wood, digging a giant hole with a big backhoe, especially if you're going to the BC horizon, in most ecosystems is quite deep and very expensive, not just in terms of money and labor, but also in terms of emissions, depending on, unless you have a solar powered electric diesel tractor, which pretty much doesn't exist. So I think it's really important, sort of as we're evaluating these things, to either evaluate ourselves or collaborate with social scientists or economists who can evaluate, or push our partners to evaluate these full life cycle emissions, because they will often help you make the decision of whether or not doing this thing is actually useful, right? And there are lots of solutions where we don't look. I would argue the great majority of these climate solutions, we're not really thinking about the full life cycle. Not just the life cycle of how much fuel we're using to implement the amendment, but for example, the industries we're creating, right? Like, this company has people working for them. They've rented office space. They probably fly around I've seen them fly around giving talks about this. And so what is the full life cycle of all of the emissions that they're spending to create this new industry? There are a lot of interesting climate solutions that are market-based, that have really large emissions burdens. When you basically say, okay, we're going to replace every single car on the road with an EV. it's a massive emissions burden in terms of mining, in terms of materials production, in terms of staffing and labor, a lot of which falls on lower income countries from which we're extracting these raw materials. And so I think it would be a really interesting thought experiment to think about, if we were able to create a system where we didn't have to, grow our resource use and our economies infinitely, what kinds of solutions would then open themselves up to us? Because there are quite a lot of climate solutions which are incredibly straightforward and fairly cheap, but they don't create jobs and they don't make money for shareholders. So like public transportation, community gardens, giving land back to indigenous stewardship. These are all, shortening the work week and allowing for remote work. These are all things which social scientists have found are kind of easy to do with the stroke of a pen or the stroke of a policy implementation that would only negatively affect the economy if people needed jobs to survive. But if they, for example, had a jobs guarantee or a universal basic income or some social services, and we were kind of okay with a steady state economy, an economy that did not grow forever and with compounding interest, that a lot of these things would be really easy to implement. I think that we have a lot of a sensation of like, in order to implement climate solutions, our quality of life is going to decrease. But actually, it's really the very, very richest among us that are responsible for most of the emissions that have been emitted over the course of now since the Industrial Revolution. And so this is work by an economist from Sciences Po, and there's versions of this in Nature Sustainability, but he has his own more detailed report called the World Inequality Report, something like that, which you can look up, where Charnel looks at the group share in world total emissions. So that's this graph on the left. So the share of total emissions from the bottom 50% of people in the world, in terms of income. And you can see that most people, the poorest 50%, are using well below less than half of their fair share of emissions. So they could actually stand to grow their per capita emissions use. The middle 40% are approximately using their fair share of emissions use. And then the top 10% is using 5 times more than their fair share, and the top 1%, 17 times more than their fair share. Which means even for a very rich country like the United States, if we wanted to meet our 2030 Paris Agreement targets, and that's this graph here over here on the right, you could see that the bottom 50% of people, fully half the people in the United States who earn under the median income, could actually increase their per capita carbon use. So and this is without transitioning any energy sectors, like just right now, they're not contributing to the climate crisis, right? Because they're essentially using their fair share of emissions. And then the middle 40% would have to cut their emissions by approximately half. And this is something that's quite easy to do without reducing quality of life. Many European countries have far below this share and have a similar quality of life as we do because their energy portfolio is different, right? Like France, for example, gets quite not a majority, but a plurality of their energy from nuclear, for example, with increasing shares of wind and solar. And so by simply changing our energy portfolio domestically, we could probably meet this requirement. And then, yeah, okay, people in the top 10%, and especially the 1% in the United States, the way that they live would have to change, private jets and a garage full of Maserati or whatever, like that, there would have to be some changes there. But I think it's important to stress that it would be quite easy for us to meet our climate goals without altering and even improving the quality of life of the great majority of the people on Earth. Okay, so that's more or less the science part. I want to transition a little bit into, I want to sort of spur a little bit of discussion about the role of researchers at this point in our kind of political history, especially as it relates to climate change. So this is James Hansen, who in 1988, this is him talking to Congress, trying to convince them that climate change is a threat for the country. And he's always had this stance of trying to make the threat clear to people that that was the role of researchers, and that really we're meant to be policy neutral, policy relevant, but not policy prescriptive. And I would say, you know, James Hansen, and also my own view, has sort of expanded a little bit here and evolved over time into this idea that policy neutrality is really a little bit impossible in this day and age. And this is just him in 2011 protesting the Keystone XL pipeline, which actually never went forward. So that was actually a campaign that was successful. It took about 10 years for them to achieve their demands, but they did eventually win, shutting down that pipeline. And one of the reasons why I say that I sort of have this evolved view of neutrality not really existing is due to my understanding of the history of science, and the ways in which we have since, you know, the 1500s, when Francis Bacon said that, you know, we must torture nature's secrets from her, that a lot of the way that we choose what to study and how to study it can reflect these kind of colonial and extractivist and geopolitical goals. For me, some of the most interesting examples of this come in the United States. So, you know, when we went to the moon, of course, researchers wanted to know about space travel and how to do it and what was on the moon. We had a lot of genuinely truth-seeking questions, but the funding came from the government because we were in a Cold War with Russia and we wanted to establish political and technological dominance over Russia. The national lab I used to work for, Oak Ridge National Lab, was built in record time from scratch within like 3 years during World War II in order to assemble the atom bomb, which involved massive technological advances, but was clearly a political goal. And you could even argue that modern medicine, you know, has values underlying it. And they're often quite good values, like that we value the lives of people who have illnesses and we want to improve them. But it isn't really a lack of value, right? And so I just have a much more nuanced understanding now of where we sit as a group of people within our social and political context. Anyway, it's maybe a bit of a controversial assertion, but I think increasingly less so. Okay, so, you know, even if you don't care about politics, politics cares about you, and I think that that's increasingly evident these days. And so I just wanted to talk about some of the ways that we as academics really have power. So here's some concrete ways that we have power and we can do things. So, you know, we're often well connected, we're very highly networked, we're organized. We often have public authority and legitimacy, which waxes and wanes with the times, but it does exist. And the public often looks to us to set an example of how to behave. And so those are really kind of concrete sources of power. When I talk about building power within the context of social change movements, I actually conceptualize it, because I'm an ecologist maybe, as an ecosystem where, you know, the agents of change, the climate movement, consists of these different strategies, organizations, and tactics that can work in symbiosis, hopefully mutualistically, right, rather than competitively. So for example, people engaging in collective action or protest, they can create these political moments that can be capitalized by insider groups. When I say insider game, I basically mean policymakers, legislators, people who are working within the existing constructs of power to change policy. And those groups, of which research is a kind of arm, right? We're legitimized within existing constructs of power. We can work to grow, protect, and legitimize, to communicate risk, develop and implement solutions, and protect and legitimize alternatives, alternative forms of energy, economy, transportation, culture, etc. And those alternatives can then resource and empower activists to intervene directly to stop harmful industries and policies. So there are sort of ways in which all of these organizations can ideally work together to amplify power within a movement. And then, underlying all of that scaffolding are things like movement infrastructure and funders, which is less interesting, but is a place where I'm increasingly spending more of my time, is sort of how do we resource ourselves, especially in the absence of government resources. So I'm not sure anyone here asked for this, but in case you were wondering, I wanted to talk a little bit about some of the change-making sort of best practices that you can start to think about in your community, whether that be your university or the community where you live as a human person, right? It doesn't have to be in this academic context. But I have several groups where I meet regularly, both in person and online. We engage in strategy building activities like power mapping, writing out our theory of change and trying to choose specific objectives and figure out how we can actually achieve those objectives, what partners do we need to have on our side to achieve those objectives, and how might we win them over, etc. And so, on campus, there are a lot of campus movements that are currently going on in the Boston area. There's a great group called the Campus Climate Network. These students are mostly focused on divestment and disinvestment, and basically kind of distancing fossil fuels from research in a variety of different ways. And they provide a lot of resources to students who are interested in that. And there's a long history of sort of the utility of disinvestment, not in really removing financial resources from this very large industry that has a ton of financial resources, but in making policy changes and narrative shifts. Oh, how do I go? Hang on, I'm having a PowerPoint issue. There we go. Another great group that operates in the greater Boston area is called No Coal, No Gas. And they're basically working to shut down kind of existing dirty coal plants and peaker plants. These types of plants provide very little of our energy, a really kind of negligible fraction of energy to people in Massachusetts. But when they run, they're quite polluting, not just in terms of greenhouse gases, but in terms of other types of pollutants as well. And so they engage in a variety of, they actually took over a local energy board, they voted in all of the members by showing up in mass to the local energy board sort of town hall where they vote people into power to regulate these industries. And so they have a lot of really interesting both political and collective action activities around trying to get some of these dirtier fossil fuel projects shut down in the state. If you're around March 24th and 25th, come say hi to me because I'm going to be in an arts related action. It's called the Climate Crisis Cabaret, and it's basically a series of plays and musical acts and poetry readings that are kind of meant to educate and create hope and create community and give people some ideas of things to do around the climate crisis. So there's the last kind of 4 or 5 pictures down here, all researchers who are participating in the final act, which is a kind of panel of scientists from the future explaining how we got to net zero. So providing some of that science-based envisioning of the future. And then, there are a lot of more standard things, all kinds of, writing op-eds and engaging with legal options, writing letters and petitions and engaging in reasoned negotiation. We also have a lot of groups active in the greater Boston area that basically follow oil executives around and the people who take money from them and go to their events and ask them difficult questions. And they have gotten some people to step down from their positions as a result of that kind of direct confrontation. This is kind of a teach-in. That's one type of thing you can do. You can build power within the local groups that you have, whether they be unions or whether they be informal community groups or groups within your faith community, etc. When people get together in numbers, they can do quite a lot. And engage in various forms of non-cooperation like work strikes or boycotts, etc. These are just other examples of protest. There's me getting arrested at the Massachusetts State House to try and get them to stop expanding fossil fuel projects. Okay, how am I and my colleagues doing all of this stuff without getting thrown into jail forever? How do we still have jobs? Well, it is risky, but there is a wide network of mutual aid and legal support out there for researchers who are interested in engaging in some of these actions and advocacy. So, and I've just tossed up some of these. I'll go through a few of them in a second. They're incredibly important. So first, I just want to quickly advertise if you need a place to start. I work with a group called Scientist Rebellion, and they have welcome meetings every week, and they have a kind of vast international infrastructure. We organize on Signal. And we have lots of working groups, not all of which are risky things. Some of them are based on communication and education. We have a talk series where we bring researchers to talk about, climate science and economic shifts and things like some of the concepts that I've talked about, but they actually know what they're talking about. And so that's a place you can start that could connect you to a lot of these other resources. If you're feeling overwhelmed, which is very normal and really a very normal thing to feel at this point in time. There's a great group called the Climate Psychology Alliance that offers free therapy, essentially. They're all licensed practitioners who volunteer a portion of their time to people. And they've actually just started a program related to the recent changes in the administration and how they're affecting researchers. So they've started sort of like it's like a free Zoom group therapy for scientists and STEM professionals. So if you feel like you would like to take advantage of that, please go to their website and take advantage of that. They're fantastic. They're really Kristen and Teddy are the people who run it, and they're really good at what they do. If you're being affected either directly or indirectly by any of the changes that are happening right now and you need free legal advice, there is a nonprofit called the Climate Science Legal Defense Fund. And then there are different legal nonprofits related to kind of STEM needs in the kind of more immigration DEI sector. If you need those resources, just please reach out to me and I will try and put you in touch with the resources you need. And they essentially, like, you can send them an email and they're very responsive. They'll get back to you and give you essentially free legal advice about protecting your employment, protecting your civil rights, and protecting your work. And lastly, if you are thinking about starting your own direct action group, but you need funding to pay for some of your time, to pay for meeting space, to pay for snacks, to pay for signs or whatever, I work with this group called the Climate Emergency Fund, where we basically just raise money and we make grants to climate activists. You have to be nonviolent, but you can be as disruptive as you want. That's fine. We're fairly risk tolerant, and we're sort of happy to support people who are trying to do things. And that's it. Those are the resources. I'm happy to answer any of your questions, and that's the end. Thank you for your attention.
Thank you. If you could join me in thanking Dr. Abramoff and round of applause, even if it's virtual. And I know we're at time,
Oh,
so
no.
I want to take more time than people have. I don't know if you have a few minutes to hang on the line if people do have questions, or
Yeah, I can hang out. I'm sorry I took all the time. I do get to talking. Apologize for that.
that's okay. So we'll let people go who need to go, and if you want to hang out for a minute and ask a question or two, that's fine too.
Oh, the name of the climate art exhibition is the Climate Crisis Cabaret. I'll try and find a link to it.
Okay. And it seems like we have a lot of thank yous in the chat, but otherwise we're good. So I just want to say a big thank you. Really appreciate that, and gratitude for all the work that you're doing. And hopefully we'll be in touch.
Sounds great. Thanks all.
All right. Thank you. Take
Bye.
care. Bye.